Welcome all to this 20th lecture of Principles of Statistics. Today we're going to concentrate our efforts in introducing and proving the consistency of the bootstrap of the mean. So for that, we'll introduce now the theorem and make some remarks about it, and then for the proof, we'll introduce some auxiliary results and indeed prove it, prove the theorem. Okay, so Theorem 1, so Theorem 1, and again, this is called the consistency of the bootstrap of the mean. Okay. And so it says the following. So if we have, so let's take a sample, x1 to xn. So therefore, IID random variables according to some distribution capital P. And we're going to assume that this has finite variance. Sigma squared. Yeah. Greater than 0. Yeah. So let us denote also the CDF, or the cumulative distribution function of a normal with 0 mean and sigma squared by the usual notation of this capital phi, which most cases actually represents the normal without, or with variance 1, but let's take variance sigma squared. So then we get the following. So then we get that the soup over T in R, we're concentrating our efforts for the real line, but all these things follow in multi-dimensions. So if we look at the probability of of this quantity here, which is the mean, the bootstrap sample mean, and the usual sample mean, and this being less than or equal to T, and of course everything has to be conditioned on these guys, then if we look at the difference, this whole quantity will go to 0, of course, as n goes to infinity, and this is Pn almost surely. Okay, so this, of course, this Pn applies to this sample here, which is what has the randomness here, and so this other Pn here will be taking care of the randomness of this guy. Yeah. Okay, so we have two sort of levels of randomness here. Okay, so let's make, as I said, a couple of remarks. The first one is that this result, we can connect this result to Bayesian statistics, or to the Bayesian posterior. Yeah? So this result is conceptually related to the Bernstein-von Mises theorem. And this is because the statement of the Bernstein-von Mises, which says that the posterior, or the norm, L1 norm of the posterior, let's see, so x1 to xn minus the, the density of a normal distribution centered around the MLE, and with variance or covariance given by this Fisher information matrix. This and this has to be evaluated at theta, d theta. So this guy is going to go to 0 and goes to infinity. Okay, and this happens Pn almost surely. Yeah. So then this implies the following, which is just that the sup over the real line of absolute value of the posterior applied to this. Okay, this minus, now we do get this capital phi. This goes to 0. This is Pn almost surely. Okay. So we see, of course, that they really are quite related, yeah, the two results that we observe here. So what is the difference? Well, first of all, let me say that, this last display comes from, something that is important to note, is that this is the MLE. And so, of course, this is for the, So this is the MLE, and so really, what is the difference? Well, the difference is that, we're looking at, so let's see. So I guess for the first one, what we have here is the sample mean. Of samples with Pn distribution. Yeah? Okay, so we have that, and what's the difference? Well, this guy is no more than the posterior, sort of thing. So posterior draw of mean, of the mean of the random variables. So, in other words, what we get here is, the posterior. So this is a random variable with the posterior being, with the distribution being the posterior, and this is, a random variable where we're going to get something very similar, but rather than having a posterior, we have just this as distribution, we have the Pn as distribution. So in fact, the Pn is no more than what you would plug in into the likelihood for the posterior. So really what we have here is a not regularized likelihood. So we're not inputting our prior understanding, but rather we're letting the data speak, solely the data speak, and no prior. So it sort of corresponds to posterior, in which we simply not put in prior, so to say very informally. And what we therefore conclude is that, so the bootstrap gives a frequentist alternative to posterior-based inference that will also will also not rely on asymptotics for the construction. for its construction. What do I mean by this? Well, I just simply mean that, we have these distributions, the two distributions that we were talking about. So the Pn here and the posterior in this second case, and these, they make sense. They make perfect sense for finite samples, and we can use, therefore, the fact that they are distributions to construct inferential procedures that again, don't really rely on some asymptotic approximation, yeah? Unlike in the asymptotic, when exploiting the asymptotic normality of the MLE. Yeah. Okay, so great, but actually, in terms of justification, we do need to do asymptotics, generally speaking. Okay, so second remark. Second remark. So, however, any justification of the bootstrap is asymptotic in nature. So in particular, it can be shown that bootstrap will essentially hold if and only if some sort of asymptotic normality holds. Yeah? Okay, so this was shown a while ago by Genet and Zinn. So this is in 1990. It's again, well, not again, but annals of probability. Okay. Okay, so then let's now move on to the proof. And for that, as I said, we need some auxiliary results. So auxiliary results to prove theorem 1. Okay. So let's start with a proposition that is actually an important result in itself. There's not really an auxiliary result for this, but rather a much more general and useful result. So this is what is called the CLT for triangular arrays. Okay. All right. So let's. So now, okay. So I will mention the statement or comment on the statement in a second. So let Zn1 to Zn be IID. It's not right distribution. So BIID with finite variance. Okay. And importantly, this is for every n fixed. Okay, so this is important. It's important to pause here for a sec. So what we're saying is that we have this sample. Okay, so you should imagine the z's to be just basically like x1 to xn. But in x1 to xn, what's happening is that we get a new observation, and this observation will have the same distribution as the previous ones. Yeah? Now, here it is a bit different, because when we get a new observation, what happens is that all of the observations will have the same distribution, but we're not assuming that the distribution of such, collection of random variables is going to be the same for, before you added this data point or after you add it. Yeah. So they are all IID, but only, for a fixed n, and then the distribution can change as n is changing. Okay. But in all of them, we ask for finite variance. Yeah? Okay. So assume, and this is what gives the name to the triangular array. Yeah. Because of course, if you have, one random variable, you're here, but then, so in the previous sort of central limit theorem, just the general we've seen, we sort of put all of the data points here, and then you get, one distribution, and then two, the same distribution for the first two, and so on. Yeah? While, in this case, what we're getting is that we have this guy with some distribution, and then we have these two guys with some distribution themselves, and then this, and so on, and so you have essentially what's called a triangular array. Okay, so assume the following. Yeah, this is a few assumptions. So one, we have that for all delta, so for all delta, we get that n times the p. Okay, and there's some PR. Okay, so this corresponds to whatever measure we have in this space. So Z1 being greater than square root of n times delta still does not send this whole thing to zero, away from zero. So we want to have this. So we want this sort of essentially this control over the tails of the distribution, and essentially, I mean, the three conditions are going to be of that flavor. So now what we're going to assume as well is that the variance of these guys, okay, and maybe when, truncating them to this is going to go to zero. So, yeah? But not zero, excuse me, to the variance. Yeah? Okay. So yeah, so we don't want to have, so we want the tails to be thin enough again. Yeah. Okay. So that, most of the variability concentrates around, compact around the origin, essentially. Yeah. Okay. So now third, we wish to impose a condition on the expectation. So now we have that the square root of n times this E, this expectation of this guy, and a gain of when you look away from the origin, this goes to zero, and then goes to infinity. So again, the same type of condition. Yeah? Okay, so if we have these three things, then what do we conclude? Well, we conclude that we have a central limit theorem for all of these guys. Yeah? And just to reiterate what's going on here, okay, so this converges in distribution, we wanted to write this guy. Yeah? So again, just for clarification, we get a central limit theorem, but for every n, we're going to have these different distributions that are not, too different because of these assumptions. But they have to, well, they don't have to be different, but, it's useful that they can be, like we're going to see now. So the proof for this can be found in, in Araujo, let's see, maybe. So these kind of things wouldn't be examinable by the way. So Araujo and Gine. Okay, and this is in the book called CLT for Real and Banach valued random variables. Okay, and this is page 63. Okay, so we won't really prove this, the central limit theorem for triangular arrays, even though it's very, very useful. Yeah? Okay, so lemma 1, so we need a couple of lemmas. So lemma 1, what is this about? Well, let's assume that, so this is purely an auxiliary result. So let's assume that x1 to xn are as in theorem 1. Okay, so I'm just being a bit lazy, really, because I could have just copied this. It wasn't too bad. So these are the assumptions on well, the first line is the assumptions on the capital F's. Yeah. Okay, so what can we conclude? Well, something very useful in practice for the calculations, which is that 1 over n, so the sample average of this guy. Okay. Okay, this guy goes to 0, and maybe we can close this as n goes to infinity. Pn almost surely, and of course this must be sorry, some issues here. Yeah, done. And this has to be, for all p. In this case, we're going to take p to go from, okay, so let's say, from 0 to 2, right? Or even including 2. Yeah. We can probably include 0, but let's leave it there. So for all p and for all delta greater than 0. Yeah. Okay, so let's try to prove this now. So let's fix, as we said, p is going to be between, I think we can include this. So between 0 and 2, and also c, which is this free parameter, is going to be between 0 and infinity. Yeah? So, well, let's say for all of these guys, we get the following. So we get that, for in the first case, so we get, and we write in x1. So this is no more than x1 at 2 times p divided by 2. And so we can apply now Jensen's inequality, this p over 2. Okay, and what we get is that, so we're going to take out the p divided by 2, and okay, so if we go slowly, let's just this here, and this, by the way, is less or equal than sigma squared to the p over 2, and so that means sigma to the p. Yeah. And this is, of course, finite, which is what we wanted, and so writing yi equal to xi to the p, and then the xi being greater than some c we have above. So, okay, letting this and also just the usual, average. Okay. Then what do we have? Well, we have, of course, that the average will converge to the mean. Okay, so that's just the strong law of large numbers. Okay, so that's the abbreviation. And then the other thing that we have is that the expectation of the y1 will go to 0 as c goes to infinity. Okay. So this is, I guess, the So because the latter is a tail of convergence series. Yeah? Or sorry, not series in this case, just need to call. Okay, so this should be clear. And what we have here then, well, we need to prove, that something goes to zero in the limit. So let's just write the usual epsilon arguments. And so let's fix epsilon first of all. So let epsilon be greater than zero, and take an omega in the set of omegas such that we have this convergence that we saw above. So this going towards this, okay? So this happens with probability 1, okay? Okay, so that's important. So what do we, how do we argue here? Well, it shouldn't be too difficult. So what we're going to do is fix the C constant. So for C greater than 0, and this is large enough, okay, and such that this guy, maybe let's write 1, is strictly less than epsilon halves. So you see what I'm doing. So let's assume this guy is very small, and let's take n also large enough, but in this case such that this quantity is greater than n. And then the other thing that we wish to have is that the yn hat at omega minus the expectation of y1, that this is less than epsilon halves, okay? So why are we assuming this, or why do we want this? Well, that's simply because if we wish to bound this following quantity, which is the sum from I equal 1 to n of the xi's, and then of course we're talking about a p that is small as before, and this is for xi in greater than square root of n. Sorry, this is with the delta, and maybe because we're talking about omegas, then it may be better to just write them out here explicitly, right? So I have this here, and then we have omega being, so in this it was, so let's see, yeah, okay, so we have the yeah, so this is just greater than, okay, so this is just greater than square root of n and delta. And this we want to bound. So what is this going to be bounded by? So this is going to be bounded by yn at omega okay, and so why do we have this? Well, because we have assumed, excuse me, I was going to point this out, but this should be a C. Okay. So because we have this condition, then we can bound this guy by the last guy, and then the other thing is that we can add and subtract the expectation of a y1. And then what do we have? Well, the expectation of y1 is less than epsilon halves, and then for this guy we have essentially convergence. Yeah. Okay, so which is what we are sort of showing here. Yeah. So this is strictly less than epsilon. Yeah. And that's exactly what we wanted, because then we have proved that for this set of probability 1, and for all epsilon, you shall have that this quantity that we were looking for, or that we were sort of studying, is actually arbitrarily small. Yeah? And so it is 0, and in this case, Bn almost surely, which is what we wanted. Yeah. Okay. Yeah. Okay. So let us now introduce a second lemma. So lemma. Okay. So this will be more general again, as in more. Well, it would be useful in other cases as well. So let's say that we have Fn going to F, okay, and this is for all t in R. Okay, so something like this, some convergence in distribution, where where we have essentially two distributions. So these are CDFs. These are cumulative distribution functions, and importantly, very importantly, the capital F has to be continuous. Okay. Then we have uniform convergence. It's not only pointwise, but actually it is strengthened by uniform convergence. And so this is very, very particular to this setting of distribution, cumulative distribution functions, in which the F, or the limit, is continuous. Okay, so of course, we never have in general the pointwise convergence will imply uniform convergence. Okay, so let's quickly prove this, and then we can go to the main theorem, the proof of the main theorem. So again, we're going to go through the usual epsilon arguments to show that this is arbitrarily small. So let's take epsilon to be greater than 0, and let take k. So k is going to be some natural number. Okay, be such that 1 over k is less than epsilon halves. Okay. We wish it to be larger. Yeah. Okay, so, and this is where the assumptions become very handy. So we say that then, because this guy is a CDF and continuous, okay, so I want to emphasize the two together, then there exists xi's that are sorted. So we have that x0 is going to be minus infinity. Then we have x1 sorted in increasing order up until some x k that is going to be equal to this infinity. Yeah? And they should satisfy that they are of this kind. Yeah? Okay, so that's sort of obvious that we have this when we have continuity on the CDF, yeah? Because the CDF has to go from 0 to 1 and continuously in this case. Yeah? Okay, so then for well, comma is better, yeah? So for x in this xi minus 1 xi, okay, in sum of the brackets here, we get what we get. Well, we can start looking at the difference of these two guys. So this is the difference that we wish to study. And so we can bound this above by simply plugging in values of the x's. And so, of course, this is bounded by this. And we can now use this and say this is xi minus f at xi plus 1 over k. And then what's the other thing that we can say? Well, repeat the calculation. Now, rather than bounding it from above, let's bound it from below. Yeah? And so by the same arguments, we can then take this here, minus fxi. Okay. Okay. So, okay, so now we do, no actual values. So we do exactly the same as in the previous line, and we're going to get minus fxi minus 1 minus 1 over k. Yeah. Okay, so now that we have these quantities, well, we want to bound, these guys essentially, yeah? So how do we bound with these guys? Well, we're nearly done because we have this pointwise convergence, right? So then for n, depending on this k and epsilon, so let's assume this guy is large enough. And such that we have exactly what we just mentioned. Everything less than epsilon halves is true for all I from 0 to this k. Yeah. So then, then we have, we can bound these guys, or the absolute value, these guys, and this is going to be epsilon halves, coming from the first term. But then the second term, we also assumed it was bounded by epsilon halves at the very beginning, so here. And so essentially, this is bounded by epsilon, and then we're only missing to bound the supremum, and that's actually very simple in this case because what we can do is to partition the space. Yeah. So let me just say it's a sup in R of fnx minus fx. Well, it's no more than the max over the i's, the different elements in the partition, and then we take the sup within each of them. Yeah? Okay, and of the same quantity. Okay, but again, this guy is going to be less than epsilon, and the epsilon will not depend on the i's or this k or x's, and so this will be less than epsilon always. Yeah. And we are done. Okay, so then we end with the proof of theorem 1. So what do we have here? Well, let's note the following. So let's look at what we have so far. So we have this lemma that talks about this uniform convergence, okay? Then we have this lemma that talks about something a bit technical. So let's leave this one out. And then we have the proposition that talks about this central limit theorem. Yeah? So what do we want to do? Well, we would like to take, in here, for these guys, we'd like to take actually the bootstrap samples, okay? And then once we have the bootstrap samples, if we show this convergence in distribution for them, and distribution under that of the, the random method of bootstrap, but not of the underlying data set, then so because we have this convergence in distribution and the limit is continuous, so as in the distribution of this guy is continuous, then we fall into the setting of this lemma 2, and we can conclude uniform convergence, okay, Pn almost surely, okay, which is what the statement sort of gives us. Yeah. Okay, so that's the idea just to start with. So as I was saying, so note that if the CLT for triangular arrays holds, and this is for the choice that I was talking about, so the choice in which we have the Z's to be the bootstrap samples, okay? Okay, and I remind you that these guys actually have a different distribution for every n, yeah? So that's why we need this CLT for triangular arrays. So, okay, so if we hold for these guys and Pn almost surely, then, as I was just saying, lemma 2 will guarantee or will implies the result. Yeah? Okay, so then really all we have to do is check the three assumptions of the CLT for triangular arrays, and then we'll be done. Yeah. Okay, so so let's check. Let's check then the three assumptions. Okay, 1, 3. Okay, so 1. What we have this quantity. So this is just the Pn of so the bootstrap sample, and this being greater than square root of n delta. Okay, so because this Pn is just the empirical distribution, then this can be simply written as n over the sum, times the sum from 1 to n of of the indicator. Xi greater than square root of n delta. Okay, so these two cancel out, and if we wish to show that this goes to 0, then we'd like to have some sort of 1 over n coming out here. Yeah. So how do we do that? Well, we can of course just multiply and divide by, say, x squared, and then just use the fact that we are in this indicator. So what am I saying? Well, I'm saying that you can take, well, you can check this, that this convinces you. Okay. This squared and times still the same indicator. Okay. And so by essentially by this lemma 1, we shall have this goes to 0 for all delta. Yeah. And Pn almost surely is important. This is by lemma 1. Yeah. Okay, so it's really lemma 1 that is going to imply all of them. Yeah. So 2, what quantity should we be looking at? So this is the variance of the xn1, for instance. So just without anything else than that. And then this being greater than square root of n, that's enough. Yeah? Okay. Okay, so very similarly, so let's write out how to, what the expression for this one is under this Pn measure, which is really what we have here. So we have 1 over n of the sum from 1 to n of xi, and then of course squared. So it has to be, everything has to be squared here, being greater than square root of n, minus then some average squared. Yeah? Okay, so this should be, so everyone should feel comfortable about these manipulations. So this is the square. Yeah? Okay, so what do we do? Well, let's add and subtract stuff. So let's write here, the first guy without the indicator. And so we're going to have, and why is that? Well, remember we want to show that this guy goes to some sigma squared, and that sigma squared is the variance of the xi's. So really what we want is to write out the variance of the xi's here. Okay? So we have this quantity, and then the other thing that we need to write the variance is that we have exactly this. Yeah? So this would be okay. And then what else we have? Well, let's write the remaining of this. The remaining of this is going to be 1 over n I 1 to n of xi squared, and then the xi less than square root of n. Yeah? Okay. Is that right? No. Okay, so I've made a mistake because I've been writing out this when it should be the other way around. Yeah? Okay, so this should be less than or equal to, less than or equal to, less than or equal to, and then here we get greater than. Okay? And then what is left here? Well, we have this guy. We still need to add one of them. And then we also have this other guy that has now not featured here. Okay, squared. So maybe we can write this as, a term, a second term, and a third term. Okay. And so we see that the first term is going to convert to sigma squared. Okay, so there is no sort of doubt about that. And this is due to the strong law of large numbers. And so Pn almost surely is the strong law of large numbers. And then what's the other one? Well, what else is going on? Well, the second term, which is this guy here. So let me just write. Okay, so maybe let's write first, second, then the whole thing here will be third. Okay. So what happens to the second? Well, the second now falls into lemma 1. Also the usual quantities from lemma 1, and so it will go to 0. It will go to 0, and this is again Pn almost surely, and this is lemma 1. Yeah. Okay, and then what about the second? Well, sorry, not the second, the third. Well, the third can simply be written as 1 over n, 1 over n, then the sum from 1 to n of xi, and then the indicator of xi being greater than square root of n. Okay, so I'm just taking the difference, and then I'm now going to take the sum of them. So this is 1 over n of the sum from 1 to n, the xi. This would be, well, we can even write this is bounded by, it's not quite that, but That's so 1 plus this. Okay. So what's going on? Well, you know, this guy again is going to go to 0 by the is this correct? Yeah, okay, so that was fine. And so now what we have here is, yeah, what I was just saying. So this is going to go to 0. Pn almost surely by lemma 1, and this guy is bounded. Yes, this guy is clearly bounded. Yeah, so it's bounded. And so therefore, it's improbability. And so therefore, all the result follows for 2. Yeah? Let's say maybe left hand side will go to 0. Like this. Okay. Good. Now the third one, what was this one sort of asking us to do? Well, it's just the square root of the expectation of the x and 1b. We wish it when multiplied by this quantity, yes, that's fine, to be bounded by, well, not bounded, but to go to 0. Yeah. And so how do we show this? Well, right, so we can simply write out what we get here, and you know, this would be square root of n divided by n, and the sum from 1 to n of the xi's, and then the indicator for the xi's. Okay. But because we have this absolute value, well, we can just take advantage and just do it all in one step and bound this guy here. Yeah. And so we, this looks pretty good, but this doesn't really have the right order to use this lemma 1. Yeah. So we would like to take out another square root of n in the denominator so that we really get what we need for lemma 1. Well, how do we do that? Well, just multiply and divide by xi, yeah, or the absolute value of xi, and then bound things. So this is going to be square root of n divided by square root of n, that will go to 1 of 1 over n, and then the sum from 1 to n of the square now of the xi's. Yeah. Just forget about the absolute value, it doesn't matter. This is it. Yeah. So now this is going to go to 0, and this will be almost surely again by lemma 1. Okay, so I hope you enjoyed this lecture, and I will see you again this week.